This is my Lab 5 magnetic braking with Faraday. So to begin, we will be using Faraday's law to find the current in each ring of the tube, the Biot-Savart law to find the force on each current carrying ring, Newton's second law to iteratively update the velocity and the position, and the purpose of the experiment is to collect data of the magnet falling through the aluminum foil tube, model the magnet tube interaction computationally, compare computational predictions and observe data, and in real life it took me 0.96 seconds for it to fall through the tube, and the simulation took 1.686 seconds. So for the experiment, we had to take a tube and drop a magnet through it after finding the north side of the magnet to properly orient it as we dropped it through, and we had to find the time it took to come through the tube, and you can see the chart of the times there, and my average was 0.96 seconds. So the observations that I had during the experiment was that it took longer to get through the tube than expected from resistance and force, and the magnet turned horizontal when it was falling through because of magnetic torque, and after it fell through the tube it went back to falling vertically. And why can't we do the experiment with a ferrous tube? The magnet would stick to the sides and not actually fall through it. So for the code, first we had to set the measurements for the tube that we found of our own tube, the length, the width, and the radius to find out how thick the foil actually was around it. Then we had to create functions for the magnetic field and the EMF, which was the change in flux over the change in time. And the magnetic field we could copy from our Lab 3, and then the EMF we had to calculate with functions that we already know and using equations for the magnet and the rings. After that, we had to calculate the gravitational force, find the current in each ring, find the magnetic force at each ring, add those together, add the gravitational force and the magnetic force to find the net force, and then we had to update the velocity and position of the bar using Newton's second law, and all this together creates the simulation. And here is what it looks like. So the black cylinder represents the aluminum foil tube, the red rings represent the increasing current below the magnet as it falls, the blue rings represent the decreasing current above the magnet as it falls, and it obviously shows how the magnet falls through the tube. And then at the end, this is the image of it, and it shows right before the magnet is about to fall out of the tube when you just have the current above. And this is the graph that it calculated with velocity versus time. So immediately when it falls through into the tube, it starts decreasing very fast, and then once it gets actually in the tube, it has a constant speed throughout until it falls right out of it, and the change is nearly instant, and the time it took was 1.686 seconds. So for the questions, if the resistivity of the conductor were reduced as close as possible to 0, the magnet would change by the induced current would increase. Because of that, the magnetic force would increase and the magnet would fall slower. If the resistance was somehow reduced to exactly 0, the magnet wouldn't fall at all. If the holes or slots were cut into the tube, how would it affect the rings? The resistance would increase because there are less complete rings, which because of that, the induced current would decrease, and then the magnetic force would decrease, and the magnet would fall faster. So to conclude, we observed how magnets react falling through a conductor and how they has to be through a non-ferrous tube. We calculated the motionally induced EMF and current. We utilized Biot-Savart law, Faraday's law, and Newton's second law in order to calculate the force. We simulated the scenario with a computational model, which had perfect conditions, and in real life it took me 0.96 seconds to fall, while the simulation took 1.686 seconds, and these measurements should be closer because they should be exact in the simulation and in real life. So that just shows that in my own simulation there's human error, either with the timing or the thickness of the foil on the tube, or any of the above, just they should be the exact same. And that is it. Thank you.